All right. Well, I guess I may as well just start. So, this is a crash course on how machines learn. So, I'll preface this whole thing by saying that I had no idea to what skill level to produce this at. So, I just kind of went with high level. I know everybody here is an engineer. So, like, I at least did do some code, and I'll show some code. But I didn't go into the nitty gritty of the statistics or the math or anything like that. I try to keep it sort of surface level, but feel free to poke me to go deeper if you want. And I'm always willing to do that. Oh, is this not going to behave for me? There we go. All right, so I'll kick it off by just starting off with a basic question of like, what is machine learning? I'm sure you've all heard the term at some point or another. I always sort of joke that I feel like every year the buzz has to inevitably die, and every year it does not. It's still kind of regarded as, I think, probably the buzziest term in the tech space today, which is a little hilarious because there's nothing really that unique or interesting about machine learning to my mind. It just takes the concept of deterministic programming and flips it on its head. It's a technique that's been around in the academic space of this world for 70 years, I'd say, maybe longer. But put simply, what is machine learning? Machine learning is just any mechanism by which an engineer teaches a computer to do things without human generated code. We're going to instead rely on techniques for having computers generate their own code using sampled data as a method of learning. Um, that's really the only thing that makes it interesting, but it sort of does highlight some of the key initial things that are valuable about machine learning to always keep in mind. The first is that because all of these systems fundamentally learn by example, data is everything. There's a reason why most machine learning engineers probably self-describe themselves as data scientists instead of machine learning engineers, because the bulk of what we do day to day is just collecting, annotating, cleaning, managing data. How do we get it? How do we get it in the right form? How do we extract the right features? How do we get everything just sort of organized so that the learners can go and do their thing? But separate from that, once you've got the data component to it, then it's much more a matter of just understanding how these systems do learn at a basic level, tuning them and letting them do their thing. Interestingly enough, there are so many different methods and techniques to build a model in this case being, I'm assuming you've heard the term, but it just basically means the output of a machine learning process. The final aggregated bit of code that comes out at the end is often described as a model. And so there's a lot of different techniques for building those models. The industry term for any of them are learners, which are just different methods and constructions for producing code out of data. Um, but the basic gist of it is understanding what are the pros and cons of each learner type. And for the most part, that's just something you learn through experience, although there are plenty of things you can read about why you pick one over the other for different problems. So ultimately, I guess begs the question of what exactly is this all good for? I always sort of joke that the evolutionary life cycle of a machine learning engineer always goes through three distinct phases. The first one being you first come into the space and you build every single problem out of a neural network because you just think it's cool and that's all you do for. Phase two is you start realizing neural networks are expensive and annoying and start building much more granular model types for various problems. And then phase three is you stop building models because you don't need machine learning for like 99% of things. And people overuse it. So what is machine learning actually good for? The basic high level I say is any problem which a human is going to really struggle to identify the rules by which to solve any one particular problem is the domain of machine learning. If you're ever catching yourself solving any problem with 100 if-else statements and lots of data cleansing in that process, then you're probably in the realm of a model. So ultimately, machine learning is most valuable for doing really large data analysis, doing things like predictive analytics, trying to monitor revenue trends and trying to forecast behaviors. And then, of course, classification is sort of the prime second example. How can I take a disparate data set and figure out what buckets does everything belong in? If I have a list of 1 million names, can I figure out which one's male and female, for instance? That's a classification problem. And ultimately, all machine learning really boils into those two buckets, regression and classification. Can I identify the number that a problem produces, or can I identify a label to apply to any new piece of data? Now, interestingly enough, because of those two categories, machine learning is uniquely suited for a couple of specific subsets of problem spaces. I highlight one because it's actually kind of what I am. So when people say they're a machine learning engineer, in general, they're talking about something very specific. And machine learning is too broad to really be accurate. You're either a vision specialist, you build convolutional nets, and you sort of work in that space. You can be a speech specialist specialize in speech recognition and transcription. You can be a predictive analytics expert, or more of a generalist model expert. In my case, most of my background is actually in natural language processing, natural language understanding. That's how I landed at Amazon. It's how I've most of what I've done professionally has sort of been in that space of how to process and manage large volumes of human language. And machine learning is uniquely suited for that kind of problem because it's sort of the classic markers of when machine learning shines. Language is inherently very messy, very changeable. There's lots of idiosyncrasies, lots of contextual rules that sort of define how we understand and process language. And it is extraordinarily difficult to try to build out those patterns programmatically. You're going to miss some. You're gonna miss some patterns in that noise. And so it's a lot easier to just take lots of data, annotate it, and let a model understand the rules themselves. Machine learning is probably most famous for its increasing adoption in the world of automation, using it for driving, for service work, or warfare, or lots of other sort of somewhat creepy applications. But the same basic rules apply. It's, can I collect a large enough data set, build complex enough features, either automatically or unsupervised, to allow the model to learn quickly how to build complex patterns for real life situations. So like with driving, can I build a model that can see one stop sign and then understand all stop signs in the future based on the amount of data being produced, even if it's missing a corner, or if it's faded, or if it's other issues. So how is this all done? It's a very wide and diverse field, but ultimately you can kind of successfully put everything into sort of two primary buckets. Even those buckets are a little bit messy because everything in machine learning is ultimately boils down to statistical math. But neural networks are distinct enough in construction that they kind of get their own bucket. And so you can think of it as just those two, neural networks or sort of classic statistical modeling, which I'll cover a little bit of both. So I'm sure everyone's heard of neural networks by now, especially the somewhat much more synonymous term deep learning, which is really just a type of neural network that I'll also get into a little bit. But the basic construction of a neural network ultimately is, can we build a model architecture that somewhat mimics the more complex pattern style matching that the human brain does? In other words, rather than building a single monolithic statistical formula that does a good job of handling matrix data, instead, we're going to carve up the problem into much smaller micro formulas and let them all interact blindly to each other and produce a single path generated answer. It's kind of the hot new thing, which is weird because it's not new at all. The first concept of neural networks is in literature in the 1950s, using a much more vanilla structure and using a type of neuron called perceptron. But they're getting more popular today for a very specific reason, which is that they're easier and affordable to build now. We'll get into a little bit about why, but to build a quality neural network requires a significant amount of compute and a significant amount of data. And prior to the services architecture world, the AWS world, that was just often quite prohibitive. So they sort of lived in the realm of academia. They would bleed into industry here and there as somebody tried to spin something out of academia. But prior to scale use of rented GPUs, it just wasn't something that was practical to do in a business setting. But now it is. There's many different forms of neural networks. They come in many different flavors, and really even all those flavors are deeply customized. And so it's kind of hard to bucketize them, but they do sort of have broad scale patterns that they end up getting slotted into. So one I'm going to sort of walk through a little bit is a more traditional feed-forward neural network, which basically means each step of the process is very straightforward, moves one into another. There's also a concept of like recurrent neural nets, which allows sort of much more fungible pass-through from neurons in different layers. I'll explain what all that is in a second. Convolutional neural nets, which allows some context association between neurons. It's very good for things like vision work, where you kind of need to know not just what one pixel is, but what neighboring pixels are, and that actually has some value to it. But yeah, so ultimately that's sort of the process behind a neural network. But the way I like to describe it is to sort of give a bit of there's sort of a thought exercise I would like to use a lot when trying to explain to people kind of what neural networks are and sort of how they function. And it's a little bit like using your friends to make decisions. And so like an example I sort of joke through, and this is obviously super, it's actually kind of inaccurate in a practical sense, but it gives you sort of the story. Imagine you have friends, a bunch of friends together with you, and you're trying to use them to figure out a question. In this case, should I go to Paris on vacation? And setting aside the fact that the answer is definitely yes, how would you use your friends to sort of help you arrive at that answer? So obviously, in this example, I'm going to put a lot of rules and constraints on what those friends are allowed to do and sort of how they can help you. But the first step in this is always taking your data, whatever you have, and then splitting it off into the most important sub-questions that are going to help you answer the core question. This is essentially feature engineering. You're going to come up with features that will help define the problem. So it's not really, should I go to vacation in Paris? It's what are the things I need to consider that will inform the decision of whether or not I want to go to Paris. So they could be something like, can I fly in the morning? Yes or no? Can I afford this trip without taking on debt? Yes or no? Is there a nice hotel in my price range? Yes or no? Is it going to be warm when I get there? Yes or no? These are all just simple binary 0 or 1 answers that in different combinations might provide different answers. Like maybe if I can fly in the morning and it's going to be warm, I'd be willing to take on a little debt to go there in the summer, maybe not so much in the winter. So like it's sort of the situation is dependent on the outputs of all of these sub-questions. So now what I'm going to do is I have my friends sort of lined up, and I'm going to give each one of them one question, and they can only answer and consider that question. So friend A, I say, I'm thinking about going to Paris and I can fly in the morning. Should I go to Paris? Person B, I'm thinking of going to Paris and I can afford it without debt. Should I go to Paris? And they can only consider the question I've given them. That's the input layer. That's essentially what I'll describe as the input layer of a neural network. They only get one set of data. And each one of these represents a feature being processed. So how's the friend going to decide what to do with this information? Well, there's a couple of things. First, because they're sort of in a silo, they don't know the whole picture. They just know what's in front of them. They kind of need to, on their own, determine how important the question is. So they know there are other things in the pipe, but they don't know which other things they are, but they just know theirs. So they go, okay, well, for me, flying in the morning isn't that important. I'll give it a low weight. I'll give it 4. For person B, they might go, well, I mean, debt's important, so we're going to give that a high weight of 9. And so they're just assigning their own individual weights, but they don't know how the other nodes or the other people are giving weights to their questions. So now what I'm going to do is I'm going to give them a scenario, and I'm going to tell them the answers to a couple of those features. And what they don't know is I actually have the answer to this scenario. I know what I would do if this was my situation, but none of them do. And so I'm going to say to the first person, can I fly in the morning? Yes, I can. Should I go to Paris? And that person is going to decide on their own. Okay, is this important? Well, I gave it a weight of 4, so I'm going to pass on weight 4. Second person, can I go this trip without debt? Well, I can't. So they just don't do anything. They get a nice goose egg. Third one, is there a nice hotel in my price range? There is. They get their weight, which they assign to 6, and pass it along. And is it going to be warm when I get there? No. Well, they also get a 0. So now what happens is all of these final values, 4 and 6, 0 and 0, get added up, and then they get passed on to the output nodes. The output nodes represent one of the 2 possible classifications. It's somebody who will either say yes or somebody who will say no, and they both get the same numbers. So the person who has to decide whether or not the answer is yes gets 10 and says, well, I think that seems relatively high. I'll say, sure, you go to Paris, and with a score of 75%, I think you're going to go to Paris on that. The no node gets the same number and says, well, 10's not that high, but I'm going to say that it's probably yes, but we'll go with like a 20% chance of no. Well, I give them the answer and say, actually, in that scenario, I wasn't going to Paris. Didn't fit my criteria. So now everybody in the group now needs to go, well, we made the wrong decision. It's time to go and update all of our conceptions. So the person who said that flying in the morning was important now goes, well, maybe it's even less important than a 4. So we're just going to make it a 3. The person who said that they can afford the trip with debt was important now seems like it's more important because they were a goose egg and they actually had the right answer essentially. So we're going to bump them up 1. And so everybody gets sort of adjusted a little bit. And then now we're going to give another example and try again. So this process of making essentially guesses through the network, giving an answer, and then correcting the weights back in the network is what's called back propagation. And this process happens iteratively over millions and millions and millions of training samples. And the idea is, as you continue to work through the network, those weights get continuously adjusted up or down until they do as good a job as they can of approximating how important each individual input feature is through the network to the correct answer. Now, I highly simplified this, and there's tons of stuff I'm leaving out, but it sort of highlights the core process by which neural networks learn. So each node is kind of in the dark. It's sort of figuring out its own place in the world by making guesses and then arriving at correct or incorrect answers and then adjusting their assumptions. By having each node sort of independently get better and better at its one job of processing that position in the path to the answer, it lets the whole network get stronger. Now, if we had 30,000 input questions and 100,000 friends that are sort of working through this problem, it gets really granular. You start developing really tight differences between sets of answers. Like it will start to matter not just that you can fly in the morning, but what time can you fly at 4, at 5, at 6. It sort of allows you to be really specific with the criteria that will help inform a classification decision. Does that make sense to anybody? Did I confuse anyone, or did I have any questions on that piece? Good. So that's sort of a high level neural network example. I'll get back into a little bit more of that later, but then I'll also talk a little bit about sort of standard statistical modeling. So what I didn't really describe well in the neural network piece, but I'll sort of double back on, is each one of those nodes are actually doing a little bit of math. So they're not actually making guesses. They have their own little model living in that neuron that makes a decision based on an input floating point number. And then they process it with their little piece of math and they make an output and pass it on. And that the weight in that formula is what's getting adjusted. So the output of that calculation will be a little different every time the weight is adjusted up or down, but they're each doing their own calculation. Statistical modeling is just one big math problem. Like you take a statistical formula, like Bayes' formula, and apply a matrix of values to it to arrive at a final probability score of any given output value. So it's a little bit easier to train. It's essentially just going one pass over each piece in the data and assigning a value based on the input, and that's it. It's also much more explainable. So one of the weird things about neural networks is, as I sort of described, each node is doing its own thing. And I didn't talk a lot about the differences between classical neural networks and what everybody does, which has deep neural networks, which is lots of these little hidden layers. The pattern through the neural network can get so complex, it gets really difficult to understand what the neural network is doing. They're classically called black boxes because every node is calculating their own answer. They're contributing to the values to the next layer, The final layer makes sort of a final determination. It's hard to know where in that process decisions were actually made. What was the most important thing? Whereas most statistical models, because they're just vanilla formulas with plug and play values, you can easily say which one which value bumped it from 50% to 60% in probability score, and how can I sort of play with those thresholds. So they're a lot times favored for problem spaces that need explanation. If you're going to deny somebody's loan application based on some of their various input features, you should be able to tell them, in fact, you legally need to be able to tell them exactly why you denied them. What were the criteria that fed into that decision pipe? So this is probably unfairly described as almost the boring side of machine learning, which is weird because it is probably the better side of machine learning. Neural networks are great when you have incredibly complicated problem spaces that are virtually impossible for humans to solve for heuristically. But they really belong purely in the realm of things like autonomous driving and market forecasting, really, really complex stuff. Most machine learning problems are really just a problem of scope. And so humans could solve for them, but it's a huge scope. There's a huge number of interconnected pieces, and it's just easier to have a model do it. But you want to know what it's doing, and you want to have it work fast and efficiently. So this is what most people do, and this is what most people should do. This is also where there's the largest variation of learner techniques. There's so many different types, from linear regression, logistic regression, Bayesian, Markov models, Markov chains. And really all of those are just fun labels for different math formulas. They just underlie a different technique for sussing out the statistical reality. Almost in general, nobody needs to know the math unless you're innovating on this stuff in some interesting way. You just need to know what each one is better at and sort of what they're typically used for. So now I'm going to walk through sort of another example using much more of like a traditional modeling approach and sort of how these things come about. And so I always kind of go with this name gender one because it doesn't require huge numbers of interconnected and subtly connected variables. Oftentimes it can be boiled down to like 7 or 8 rules, but sometimes it's hard to suss out exactly what those rules are, and some of them duplicate. And so like we imagine trying to identify genders to names, we have a bunch of sample names and we can assign values to them. There's a reason why I use this example too, which I'm going to get to in another slide, and you'll see why in a minute. So I take these names, these sample names, and I'm going to carve them up in interesting ways. That's called feature engineering. I kind of just like bleeded over that a little bit with neural networks, but a lot of what machine learning engineers do is feature engineer. We're given raw data, and then we're told we have to be able to design models around it. Oftentimes, one of the first things you need to do is figure out good ways to carve up that data. The data itself isn't that meaningful. The difference between Michael and Stacy is just letters. We want to be able to pass those letters into a model in an interesting way. So we say, okay, we're going to run experiments, feature experiments. So I say, maybe the first and last letter matters, or maybe the last 2 letters matter. So we're going to start with the last 2 letters example and say, okay, I'm going to carve up features. And instead of giving the model Michael, I'm just going to tell the model, all you care about is that the last letter is L and the second to last letter is E. Doesn't matter that it's Michael, because I don't want you to be able to tell me that Michael is male. I want you to tell me that a future name that you don't know whether it's male or female by learning the rules that define this process. And so we carve up these examples of all the different letters and assign truth. Truth in this sense is just annotating samples with the answer. So LE is not female. YE is female. LU is not female. Just being able to give that data in sort of a consistent structure. And we're going to pass those values through the model. And the model is quite literally just going to build under the hood a matrix of assigned realities. How often is L and E resulting in the truth of male? And how often is it not? And then build this a probability score across that one input feature. And then let's do the same thing for another feature and another feature, and then it aggregates those statistical features into a final score. How likely is it one or the other? So in a second, I'll describe why I like that example, and I'll also show an example of that working in real life. But I always like to quickly cover sort of like a lot of the nonsense around machine learning. There's so much buzz and language around machine learning and what it's going to do to the world, and it is hugely powerful in the right setting, and it will have dramatic impacts in a lot of industries due to automation and other factors. But it is also worth noting that it's not magic. It is just learning from data. So data is everything. it does mean that there is no problem too complex. It's not an isolation problem. It's just a collection problem. Can I get enough data, and can I break that data down in enough abstract ways that I can teach a statistical model to learn patterns from it and understand what are the important things about it? It's not that it's a stop sign. It's that it's red and it's shaped like an octagon, and like you're learning the features that outlie a truth, so that I can then generically apply it to future scenarios where it's not identical, but it does have common features. But the catch to this, though, and this is another reason why I like talking about that sort of named gender example, is it highlights one of the interesting problems with machine learning. The data is the problem. Collecting data is very hard, sometimes prohibitively so. There's only so many free data sets. And so a lot of what we do with our time when we're building models is just constantly trying to collect data. There are billion-dollar industries entirely oriented around collecting and managing data sets. Facebook essentially is just a data company. The fact that they have a social network is tangential to the fact that all of their money stems from their ability to collect and then sell data. What's the problem with that? The problem is, unless you literally have everything, all data is biased. There's sort of this inevitable reality that we like to think of data as an unbiased source of truth, but the reality is that data has a bias just like anything else. In fact, it's a little more insidious because people think it's unbiased. And so when we build models off of a million records and then just point to it and say, well, the data said, it's too easy to dismiss the problems that that can induce. You know, if I have a million names and they're annotated as male and female, but I've missed 5 million names that are also there and might have very different rules, I'm going to build a model that looks really confident, that actually looks really good when I give it lots of examples, and it has this sensation like it's doing something valuable, but where there are errors might be really problematic in practice, in production. So that's one of the big core problems, and that's why ethical AI is starting to become like a really important thing that's emerging in the industry. How can we better safeguard the space to make sure that engineers aren't just washing their hands of their responsibility to manage good development by just saying the data is the data? You know, how can we put some guardrails on this process? And then that's the most important catch in my opinion, but there are other catches. For one of the bigger ones is that there's none of the existing technologies that are at work, none of the existing learner structures have any sense of creativity. Even ones that look really creative are not. They're just statistical outputs. So that has a problem, in training. You can't give a neural network or a model 5 examples and have it just get it. It's not going to be like, oh, okay, I see what you're doing. Like it has to see the universe of possibilities, and it will very slowly and gingerly learn the features that are part of that. There's no creativity in the process. And it will also learn nothing that it has not seen. It's not going to make any additional leaps beyond the data it was given, which is extra problematic because for the most part, all statistical models are built to always produce an answer. There's no such thing as I don't know in machine learning. And so it will not give you an accurate answer if you give it new data, but it will give you an answer. And so there's lots of other things you need to protect against that issue. And then of course, they're expensive, especially neural networks, but collecting data, storing data, managing data, processing the data is just expensive. You know, AWS, GCP, these services have made it cheaper because I can rent things now. I no longer have to buy physically GPUs and have 50 of them running in my closet with an air conditioning unit, but I still got to pay for it. And so it's come down from millions, but it's still thousands to build these models. Any questions about any of that? I will actually show some code running too, which is always fun, but good. All right, we're good. All right, so let's see some code.
Sorry, I have a quick question.
Shoot.
It just dawned on me, we obviously all generically have inbuilt preconceptions of stuff. So how do you overcome that from when you're architecturing something some kind of design? Obviously, like you could get some kind of developer bias on a certain way you plan something, right? So
yep.
Is that an actual thing?
It is. It's a major problem. I mean, there's lots of real world examples of models that perform very well in validation, very well in parallel shadow testing, get out to production, and then go haywire. Because as soon as they encounter real world problems, um, all of the biases in the data, the biases in the feature engineering process, the biases in the model construction suddenly come to light because they encounter scenarios, examples that were not part of the developer's thought process as a part of the developer's data collection. So yeah, it is a big problem. Oftentimes companies try to solve it with just volume, which is why, I mean, GPT-3, for instance, is an example of a model that's getting tons of attention today. And one of the things that has caused it to get attention is it is massive. It's probably the most expensive and biggest model ever built. It was effectively built on the internet. And so that is oftentimes what a lot of companies strive for as a way to try to suss out and solve for biases, is that if we just have enough data, we will find the edge cases, that we won't miss something because we'll run against it eventually in the set. The problem is in a practical sense, you just never have all the data. I mean, even GPT-3 isn't literally the internet. It's getting a huge cross-section of it like Google does, but it's missing stuff. And it doesn't have any conception of new data. What will it encounter that it can't collect in the future, that is just all new? What are words that humans haven't spoken yet that we'll invent because humans are creative? And so, yeah, it's a problem. It's why, AI is expensive and requires constant iteration or revision. These things are never really that flawless.
That's a problem with like human data too. Like I worked at this. I didn't work on the AI part of things, but I worked at this AI startup where we had these chatbots, and this particular stuff was for L'Oreal, so it was like skincare regimes and stuff.
Okay.
And our researchers were training models to do certain things, and it turned out we didn't have enough information about Black people, other ethnicities. So you couldn't actually make good recommendations for skincare, which I mean, that's like a little less serious of an example, but I know that like not having data from all different ethnicities is an issue.
Huge issue. I mean, it's funny. You did give an example that is in and of itself already a major problem, because it's going to have an impact on the business and it'll have a major impact on the customers, but it also is a little silly. There are huge implications in that exact same problem space for things like face recognition, which police use, which the military uses. I mean, just imagine if it's able to granularly and very accurately identify white faces and will constantly blend and miscategorize Black and brown faces. You can imagine the chaos. There are even other silly examples in the vision world of exactly that. There was a viral video that went around a couple of years ago of a CNN company that was selling cheap IoT neural net models for detection for silly stuff like faucets and for paper towel dispensers. And the videos were of Black and brown and POC people like not being able to make it work because it didn't detect non-white skin. It's things that you don't do on purpose, I hope, but it just highlights the risks of depending on data to guide things with not enough oversight. If you're not thinking enough about the problem space and you're just like, hey, I just got this great face database from MIT, I'm done with the data, let's build the model. Maybe review your data and analyze your data, consider the problems and think through all the different stats. Don't let the customer figure out that you didn't think enough about this stuff.
Like two things. You said talking about like the face recognition thing. I remember several years ago when that was sort of the new thing that everyone was using. There was news that went around that was pretty viral where they had taken this face recognition software to an Asian country. I don't remember if it was Japan or China, but like it recognized them all as the same person.
Exactly. It's crazy, right?
Because like I guess they didn't have enough data. They probably just went off what they had. But I thought because it went around as like, oh, the software makers, automatically the software makers are racist. Whereas they might not have been. They might have just not had enough data to work with, like you were talking about. Like, and that might not have been purposely making it so that they think all the Asians look the same.
Oh yeah, I mean, ultimately, I think that's the big. I've talked about this in a different context, and it's risky for a guy like me to talk about it. But I like to believe the best intentions of people. I think most people that cause these problems are not doing it intentionally. They're not themselves trying to architect flawed, racist, or misogynistic tools. But yeah, it's a failure of imagination. They think they've got the data, and they didn't think about it critically enough, and they didn't really examine the problem space. They didn't go, well, I collected a facial data set, but I collected it in New York. Do I have enough? Or I collected it in Boston. Is that a representative enough sample that I'm realistically going to get what I need to build an international cross applicable model? And so, yeah, I think that's the core of the ethical AI movement is not saying that the engineers are the problem. It's the process that's the problem. We need to think a little more critically about what we're doing and not be as cowboy coterie with it. Like, hey, I've got a data set. I'm good. Let's build a model and ship it. There's implications in that.
And most recently, Facebook, at the beginning of COVID, they switched their flag system from real people to their AI system, and it immediately failed. Like, it started flagging. Yeah, it immediately failed. It started flagging everyone. You could post a picture of kitties, and it would flag it as porn. You know, it was completely failing across the board, and people were getting banned just all over the place. And Facebook's like press announcement was like, "Hey, our bad. We stopped letting people look at it, and we let our AI look at it, and apparently our AI wasn't as smart as we thought it was."
I mean, that actually highlights another interesting problem with any statistical modeling is unless you can critically analyze the outputs of the model, which a lot of traditional, I sort of highlighted that a lot of traditional statistical models allow for that, at least at some level, where you can sort of dig through the input variables and see what kind of weights they've been assigned and sort of just back out the values of the formula. Neural networks are notoriously difficult to do that for, but they're very accurate. And so people sort of still want to use them and want to rely on them, but it can create fascinating problems. There was a paper that came out of MIT a bunch of years ago that they had produced a model that was showing incredibly accurate results in classifying the difference between a wolf and a dog in a photo, which is a notorious problem in vision modeling. Because they look very similar, they carry very similar attributes, but yet humans can very quickly distinguish them. And so those are the problems that most fascinate AI researchers is when do machines suck at something and humans seem really good at it natively. And they had built a model that was outperforming even humans. And so that was big news until they started to dig into the model and sort of look at the activated weights. And they actually found that what ended up happening was it was making decisions almost purely based on whether or not there was snow in the photo, because almost every wolf photo they had in the training set took place in a cold climate and they had snow in the photo. And that's something that they didn't start noticing until they applied it to real world scenarios. And so like, there's so many examples of that kind of problem that it's something that we spend a lot of time trying to think about and probably still don't have great answers for.
So you might have answered this question in terms of the data biases, but like what I don't want to say what exactly, because obviously if you knew, you would be a lot richer than you are now. But what are like examples of the source of the bias? So like in my head, I have an idea of the data itself or these are the two things that I can think of right now. The data itself is biased. The person who produces the data is biased, thus the data is biased. Then the person who collects the data is biased, and thus the data collection is biased in the sense of it's just simply not the entire data set. As you said, it can't possibly be. But obviously, those are two very different problems that require two very different solutions. So I guess what the question is, which of those two, and if there are other scenarios that contributes to data bias, like at the very least, could you talk about the scenarios that contribute to data bias?
Yes, I mean, ironically, one of the biggest problems I believe is the biggest issue with data biases, is the most insidious one because it's the hardest to solve for, is that most data used to build models these days is not actively collected at all. So it's not that there's a collection bias. It's not like there's a bias in the person collecting data or a bias even in necessarily the people providing the data. It's inherent cluster biases that happen in the ways humans naturally congregate and produce data. So GPT-3 is an interesting example. There was a couple of post examples built on applying similar question and output sets, but substituting in male and female pronouns and values, and they would change. And it was clearly producing notably misogynistic differences. Ultimately, the reason for that is a lot of common language interaction in GPT-3 is probably based off of like Twitter posts. And so it was the problem that the data is biased is probably because the internet and the people who commonly post on it with gusto are themselves misogynistic. And so it creates sort of these weird environmental problems. Where are you getting your data, and what do the people who produce that data typically act like? You know, if you collect data in Boston or Los Angeles, you're going to get different results just because of the natural geographic and cultural difference in the places. And that's, it sort of highlights why I said the industry tries to solve it with volume of data. The problem is even that's not always a solution. Like, I'd like to think that, for instance, the internet isn't majority misogynist, but just that misogynistic people are loud and produce voluminous content, if that makes sense. And so also the problem of like, how do you moderate volume? How do you moderate production? How do you moderate historically over time? Did values different 5 years ago versus a year ago? You know, to try to get these large data sets, sometimes we'll collect way back. You know, I've built financial models where I'm trying to collect data back to like 1980, and I constantly will stress with like, is this data actually useful, or am I going to build a terrible model that works well in validation? Maybe it carries, but it's hard to really know. And so there's just constant problems in sort of how do you curate data. A lot of times people will try to solve it with their own brand of like data analysis statistics. Like, can I make sure that I'm never getting more than X number of samples from a single source, and I'm never getting more than X number of samples from a single aggregate zone? Can I make sure that I'm distributing enough between geographies? And so trying to build sort of ways to slice the data that gives you a good cross section, but it's really hard to be foolproof.
So that brings up well, I won't say it brings up, it's also another question that I had in mind. Is so from pretty much the way the software industry solved that problem in other ways, in other places, is, you know, we're not going to front load the software project. We're just going to build whatever we build, and we're going to put it out into the world, and we're going to build it iteratively. Is that even practical? Is that even possible for like machine learning type? Like, in not even in the sense of actually, can you physically do that?
Right.
You know, is it socially acceptable? I don't even know how to describe it, but like,
I sort of get what you're getting
the
at.
culture, yeah.
I don't think I have a great answer. My instinct is no, but you can make a pretty strong case that that is true for existing heuristic development. How many times do companies deploy rapid products that are not accessible, for instance?
Right.
We constantly, as an industry, to our detriment, produce problematic things that, because they don't impact the majority, they don't get tremendous amounts of attention. It's one of these things that I feel like just broadly requires cultural shifting. It requires a little bit more thoughtfulness and deliberateness about how things are built. And it runs very counter to how the industry is constructed. I've fallen victim to it. I will definitely at times bias towards speed of delivery versus hardness of delivery. It's just the nature of the startup world, but you have to admit that that's problematic. And that, you know, I think the industry needs a bit of revision instead of how it approaches product development to some degree.
Nice. Right, thank you very much.
Cool. So I'll just run a couple of simple code examples to sort of wind this down, just so you know, we're all engineers, so you can sort of see it in action. And so this is a sort of a lesson that I put together forever ago. It was designed to essentially teach people how machine learning sort of functions without having to actually write code. And so I sort of have this simple example put together that sort of piggybacks on the names one that I was referencing. So very simply, just going to import this giant CSV and just sort of slice and dice it into training sets. And so oftentimes when you're building training data, you want to do your annotation. You know, I have this big single unmunged set of data, and I got to carve them into different sets. And so now I'm going to take all these names and put them into male and female buckets. So you'll notice I have, you know, roughly 50,000 or so names in this set, indexing pretty hard for female over male. That is in and of itself potentially a problem, but we can deal with that later. Maybe we'll limit it, cause other issues. So let's run our demo. So we've got that data carved through. We're gonna run through a couple of different steps here. So first, we're going to, like I said, put it all into a single sample set, and then we're going to carve out a training set and a test set. The reason why we do that is we want to make sure that the model at least kind of performs in vitro. So once I've built the model, can I run it on a couple of samples that I have very clean answers for, and it does okay? And oftentimes that threshold is just something you play with. I often go with like an 80-20 rule. Take 80% of your data for training, reserve 20% for validation, and then you know, depending on exactly how big your data set is, you can play with that a little more. Each one of those samples, both training and testing, is going to go through feature extraction, which means this is all the engineered features that I came up with. And so we're going to, for instance, in this example, I'm going to grab the first letter of every name, the first type, whether it's a vowel or consonant, the last letter of every name, the last type, and the length. And it's just, that's it, 5 features. And we're going to just say, does there seem to be any statistical significance in these features? Do they seem to have any proving value? And so when I run this against roughly 50,000 names, I've carved out 20% of that. So roughly like 10,000 names as testing, it gets about 75% of them correct. So whether or not we think that's good enough or not, I mean, industry, like in actual industry practice, that's not very good. You hope your models really perform like in the 90+ range, but it's not terrible. It's not a coin flip. It's not 50-50. So we'll call it maybe okay for a first pass test, and let's run a little game. Let's experiment with it. Let's see how it goes. So somebody throw out a name.
Frank.
Hard.
Male, 100%. What do you think? Yes, no? Somebody else throw out a name. That's not male.
Pat.
Yeah.
Pat.
Saturday Night Live.
Male, 95%.
I was going to say Jody.
Jody. Let's do that. Female, 88%.
My mom is Jody with an I.
Well, let's try that. Let's see if it makes a difference.
I can confirm I'm in touch with my female side though.
Jody with an I, female 91%. Slightly more confident when you end with an I.
Courtney in the Caribbean is typically a male name. What happens there?
Perfect example of potential data failing. Where did I get this name set from? Is it collected mostly from, see, 93% female. Seems very confident.
Not from the Caribbean.
What about Ashley?
Ashley, another good one.
Another one.
Yeah, you're in the South. That it's 50-50. It's game all the way across the board for who that belongs to.
Female, 96%.
Interesting.
The data? Probably, yeah. Where did I get this name from? Did I pull this out of like, Northeast Boston Dictionary or something?
Interesting name, Coyote.
Coyote?
Yeah, Kayyode.
Like that?
DE.
Female, 96%.
Yeah, that's wrong. Well, I don't know if that's wrong, but at least my brother would say.
I think it's good to say it is wrong. And ironically, the confidence value is what makes this the most interesting to me. Ultimately, these models are supposed to produce decent confidence value. So if you create, the nice thing about machine learning models is they do allow for the concept of ambiguity. If you produce a name that does have decent divide, like it has, a 60-40 split between male and female, it should reduce lower confidence. And so as an engineer, you can build in thresholds to say, if it doesn't reach sufficient confidence, call it a null and request answers. If it's getting really confident though about things that should be ambiguous, it's probably a data failing.
Can we finally settle a bet? I'd like to know the gender of nachos.
Oh, of nachos.
Oh, really?
Nachos. All right. Let's see. Male, 96%.
I knew it. I'm going to go tell her right now.
What about taco?
Taco. Ooh, very inconfident female. 58%.
That's yeah.
Sorry, so I maybe missed this, but where do you draw your data from for this though? Like,
so this is literally I grabbed a set of all names, the most popular 50,000 names given to kids in the U.S. in the 1990s, which you can get from the census. So it's kind of to highlight the point. Like, where do you get the data from? That really matters. Did you collect it from some public set? Where'd that set get its data? How is it collected? That's where I got this data.
Yeah, it's really interesting because wherever the geolocation of that data comes from could be,
exactly.
definitely different to a different location.
I think that's like super important is that like knowing what that data contains, like what exactly in the CSV. So as like a data engineer, do you ever like just get a printout of what's in the data so you can just see what's in there, like peruse it? Because I know like
I don't think I've ever done a printout, but I've definitely
like it's an API. It's not AI, but my school's website, I can tell exactly what they did when you pick like a home language. They give you options for a bunch of languages, but there's also some weird ones in there. There's you can do Old English or Middle English, Ancient Egyptian. So I know what happened. The API that they grabbed for names probably was just like every language that's ever existed, and then they parse that into like a selection so you can pick like your home language. But I'm like, I imagine
they ordered them by prominence, and then
yeah. But I'm wondering if that same thing can happen in like data engineering. I would assume is that like. You think you've got a list of languages, but it includes like dead languages.
I mean, as data engineers, we like to think that volume solves the noise problem, but that really depends on it truly being fringe. Like if you have 1 million samples and 30 of them are bizarre, a good model will successfully ignore those. But if you get 1 million samples and 40,000 are bizarre, you're kind of itching into the realm of the model still going to consider them. They're still statistically prominent enough. They're on the tail for sure, but they're not ignorable. And so, yeah, that is, I mean, data pollution is a known problem in this space. It can definitely cause some weird edge cases in production models.
So, go ahead.
I was just going to say that made my ethics bells go off. I imagine that people might pollute the data to get the results they want to like to show. I don't know. Yeah.
It's especially a problem in more modern modeling techniques like reinforcement learning, which you can actually create online versions of. So they'll continually learn from newer interactions. Microsoft sort of famously launched a Twitter bot that was a reinforcement-based neural network that rapidly was taught to be very racist by nefarious Twitter actors, and they had to take it down. And it's like, you can definitely game these models in interesting ways. In fact, one of the more common ways to play with neural net gamification is to create adversarial neural nets that are trained to build examples that will break the existing neural net. And so like people have done this in image generation neural nets to create images that look to the human eye exactly like something else, but have engineered the right features to confuse a monitoring neural net into thinking it is something different. So you can take like a picture of a turtle and convince a vision model that it is a gun, things like that. And all they've done is tweak certain pixels in the right spaces where they know the neural net is looking and indexing on and will successfully trick it.
So I have a quick question about creativity, I guess, in the language processing, natural language processing space. So from my understanding, the way spelling bee champions actually know words, they don't really know the words per se, is that they understand the base of the language. So they understand how the words are constructed, and so they hear the word and then they deconstruct it from where it's supposed to be, and they build that word in their head letter by letter, and then they attempt to spell it like that. is that considered something that would be in the creative space that a machine learning algorithm would be able to do or not be able to
That's
do?
pretty much how NLP works today.
Oh,
for the most part, language models don't really have any true conception of the language that they're working on. They just have a conception of the construction rules that humans use to build language, which is also why language models usually need to be very language specific. They're trained on English, they're trained on French, because the rules that construct the languages will shift dramatically from language to language. But as long as the training data is within a single language, in theory, most of what it's doing is vectorizing words into essentially numeric representations and just looking for typical patterns leading into things. Like what kind of adjectives, nouns, verbs lead into discussions of organizations, leading into discussions of people, leading into discussions of pets, and just being able to identify what are the markers that sort of help the model determine that one individual token is or is not a certain entity, or that one individual word is or is not a noun or a verb. It's not actually, it's not like consuming a dictionary and going, hey, anytime I see this, it's a verb. It's trying to find those patterns in the language that are consistent across every type of verb, every type of noun, every type of organization, which can create funny and interesting problems when it comes to like slang. Like these models will build really good rules, and then humans being humans will come up with hilarious new ways to make verbs out of things and really trip up these models. And so constantly rebuilding them is actually important in a lot of NLP world.
Something I just thought of, I guess, sticking on the subject of languages, not all languages are created equal in terms of their own adherence to their own supposed rules. Like French, I know, like it's just a much more linguistically consistent language in terms of sticking to theme than something like English, which is a hodgepodge of like 6 or 7 different things. So I imagine a scenario where someone develops a model using one language, like, oh great, I can use this for everything, and then they find out, oh wait, no, this does not actually apply outside of the very specific domain I have trained it on at all.
Oh yeah,
I guess that's a frequent problem.
It is a frequent problem, and it can create specific problems in languages that kind of translate well from a feature engineering perspective, but have specific nuances. Like not to be a dead horse, but a related problem is moving into a non-gendered to a gendered language can cause interesting problems when converting back and forth. It's an interesting issue. Oftentimes, like anything else in this space, we just try to solve it with volume. If we've just collected enough data in these languages, we think we've covered the corner cases. We found the slang. We found the formal versions and have built a comprehensive enough rule set, but rarely do we actually.
Is there, well, you mentioned that there's data cleaning. I don't know if you mentioned that there's data cleaning efforts, because you constantly say, the general solution is to collect volume and then hope that the data itself will either cleanse or pull out the problems that you make or come across. What other techniques can potentially be used to solve that problem? And if you could talk about, I guess, the I don't want to say how human intensive is it versus the collecting in volume, which I'm assuming is significantly less human intensive.
Yeah, I mean, so other than volume, there's really mostly 2 things that we'll do to data to try to make it work. The first is data segmentation, which is, like I said, kind of almost a statistical exercise, but often is mostly manual. We just try to make sure that you're getting the right distribution of data types across them. Like if you, for instance, you're building a language model, you don't want to get 1 million 3-word micro sentences and only a couple of longer sentences. You want to make sure that you've got a nice distribution of types, nice distribution of sources. And so we'll spend a lot of time doing like source management, output management, and output structure style, looking for good diversity in the types of data being considered. And then the second piece is limited data cleaning, but only in cases where we know the problem is a problem. So doing things like getting rid of hashtags and tweets, or getting rid of like things that we know are going to be recurrent and are just going to cause problems for the model. You'll do some like basic rule cleanups. But for the most part, that's usually kind of it. You don't want to do too much of the data because, like you said, then you're just interested introducing your own biases and problems there. But if you do anything more than those two.
So like with your talk and stuff, it made me think a lot about, you mentioned Google, it made me think a lot about Google Translate. It's like you put in something in there, and most people just pay attention to the first thing that pops up, and it says, you know, you're translating something from English to French. But if you look, there's usually like 6 or 7 options. It could be this is most likely it, but it could also be this, or this. And it gives you the option, if you're a native speaker, to like upvote and downvote which one you would actually use. So is that kind of like what you're talking about? Like, so if something gets downvoted enough, cleanup would be like, let's remove this as an option. Everyone who's a native speaker says no one says that.
Yeah. Crowdsourcing data management is yeah, I should have referenced. That's another common technique is just put it to people and do it at volume, another volume problem, and take the majority average of solutions. So essentially why Mechanical Turk is really popular in machine learning space is you just keep firing problems at a group large enough and then take the cross section. That has its own problems though, because those are very gamifiable and it happens, but hopefully you just hope that it's not a big problem.
So when the CAPTCHA tells me to identify all the street signs in these 9 images, you know, which robot am I making super smart?
Right.
And then I start questioning myself, is that a street sign? Is that
right? Is it?
Am I the robot?
Am I being
the worst is when it's like like click the boxes and one has like 1/30th of a street sign and you're like
right?
Sweating.
Does that count?
And then it still tells you you're wrong.
Time.
What's funny is that data is like when you're doing recaptchas, you are training machine learning models right there.
So what's with the recaptchas that don't ask anything? Like I've heard lately, I've been seeing a lot where like it pops up and it says protected by recaptcha, but then nothing happens, and then you.
They don't like your data. They don't want you to tell them anything more.
So from my understanding, well, one of the recaptchas, I guess the earlier ones, their intention was to scan a bunch of books and then have people using the recaptcha have them actually put the text for the book, and so that they could I don't remember exactly how it worked, but I guess they could collect they could convert the scanned book into text.
Yep.
Or something like that. Is that something that, because that's when I was just like, I'm cool with recaptcha because I'm actually helping for this.
Yep.
But I don't see that anymore. You know, do you have any idea what happened to that project?
It'd be basically that it's good enough now. They don't need more data. Like this sort of an interesting collection issue is usually once models start to get to a certain tier of accuracy in like the upper 90s, it's better to tune the model than it is to get better data. Like you've got enough that you're seeing very limited errors. And so you go, okay, we've got our data. Now we're going to make the model better. The actual construction model, the hyperparameters, the tuning of the model, build process better. And so that's honestly what ended up happening was they didn't need any more text data. Now they need more image data. And so they've moved into sort of image collection process as opposed to text collection process.
So when there's no more images, we know they know everything about us.
Yeah, when they move to video files and they want you to start annotating moving images, that's when things get fun.
Will the other side of it have affected it too? Like that whole, like every time someone makes something idiot proof, along comes a dumber idiot. Or like,
yep.
The idea behind that was to keep bots from like getting into a website, right? And then I guess I would imagine that eventually people were able to program bots to read that recaptcha image and type in the right text. And
it's essentially a real life version of an adversarial net. You're creating an environment where people are trying to break this stuff, which actually produces better data. Now they can give you more niche examples, more confusing examples, and then they get better annotation. Like it sort of continues down the path of like more and more niche data that is actually hard to game.
So
I like the ones that make you solve an equation.
Right?
Oh, you don't?
Yeah.
No. You might go to hell on that one.
There's
go
a
ahead.
neat one. It's got like it's usually an animal, and they're like, rotate this until
I was about to say the same thing.
That's the new trick right now. I'm
Right.
just like, maybe I like upside down puppy. You know.
Well, that's what I was saying. Like, all of those are super obvious, but like here recently, I've been wondering what they're like looking at on the ones I've seen on some websites where it pops up and it says like protected by reCAPTCHA, and it gets a little loading sign, and then it just goes into the site. It never asks you for text. It never asks you for anything. Right. Like, I'm always wondering, like, what is it basing its thought process on that I'm not a bot at this point? Or the ones that you just click. It says like click here if you're not a bot, and you just click, and then
Yep. By the way, I didn't even realize that you guys were all chatting while I was talking. I'm just reading through them now. So, you asked anything, that's why I didn't respond.
We were just bullying you.
We were just
right.
Yeah.
That's where all the tomatoes went. That's where all the tomatoes went.
I didn't get any. Come on.
I guess a quick question about this high level still, because I don't really know this stuff, but the difference between the neural nets and the just doing the calculations, like you're saying with like, say like a Markov,
Markov chains.
The neural network's more expensive because like in both cases, you're always reducing to get to a result, but I guess the neural network, it's spanned across many machines, and that's why like you're bringing it back and constantly reducing and then going back out, or why is it more, is that why it's more expensive? Or?
No, it's actually, so I didn't talk a lot about exactly how neural nets train in practice, but they actually don't, neural nets see the same samples multiple times through the training process, and they'll just munge the way the feature extractors work. They'll actually just munge the data slightly in new runs. So every training in neural net goes to multiple runs called epochs that just keep running over the data until the model gets tighter and tighter. And it's literally running a validation set continuously against the model. Is it getting better and more accurate as I go? And it's trying to optimize for the most accurate possible output. So that, whereas statistical models just run once. They go, I have my data, I built my matrix, here's the rules, and we're done.
Okay, gotcha. Okay,
in fact, one of the interesting, just sort of practical hallmarks of the difference is if you build a statistical model on the same data, it will produce the exact same model every time. That is the model. Whereas neural networks will actually build new and different models every time you rebuild them. They'll be slightly different.
Makes me think of SETI. If you remember SETI back in the day.
SETI.
Yeah, it was.
Search for
you could loan your computer if you weren't using it. You could loan your computer to help them like listen for aliens in space.
I had that running on my machine all the way up until like 5 years ago.
Yeah,
they're still doing it, but they're doing it with protein folding now, so that they're trying to find protein targets for drugs.
I actually right now there's a bunch of these now. I have one running that does my computer site shared cycles go to COVID research. There's a bunch of these now.
Yeah, like I remember, well, I don't know if it's famously, but I remember like when the PS3 came out, it came with Home, I believe, at Home, where it did I think it was for cancer research that you just run it in the background, because at the time the PS3 CPU was famously pretty good in comparison to other commercially available CPUs, and so, but yeah. Is that even that project is still running, right?
Like, I think it is, yeah. Home? Sounds familiar.
The big takeaway from this is just how actually nerdy Bryan Healey is.
How what?
Nerdy.
Nerdy? Oh, geez, yeah.
Nerd.
Massively nerdy.
So much.
Right?
You're showing us all these pictures of like chopping wood and stuff. Meanwhile, you're just doing math all day, Bryan.
What I learned is that I want to take Bryan out for drinks.
Right? I am very fun.
Yeah.
I want
the bow tie
to like go to college for me now that
take the tie off.
Oh, it's the actual book. You can actually. I want to learn.
It's not clip on, Chad. You don't.
Am I a peasant? Of course, it's an actual bow tie.
I'm sorry. Oh my god.
I just learned about the bias here.
Right.
I thought it was breakaway. I thought you were like, okay, party time.
Party time.
Wow.
Tearaway tuxedo. I'm down with that.
Oh.
But no, really, Bryan, I've been trying to get the gist of this ML stuff for years. And this is by far the best sort of like what you need to know, concise overview. Like my partner was just asking me about it, and I was able to say sort of with confidence what you were talking about. I'm like, yeah, that makes sense. So
awesome, good. I'm glad.
It was really good.
Post it on the internet, please.
Put it out there.
Have you had a chance to like run any of your AI stuff on like any of the freely available quantum computers like IBM's Q or anything like that?
No, I haven't yet. I have early access to some stuff, and I just never really got around to playing with it. But
like,
the funny thing is, I mean, I still feel like I could talk meaningfully about this, but most of my life now is dealing with people.
And chopping wood too, though.
And chopping wood, of course. Yeah.
I don't know. I guess I'm a nerd because I got excited about it. I mean, like it was a walkthrough, and you built a JavaScript AI tic-tac-toe thing.
Oh, that's cool.
And you got to run it on IBM's Q quantum computer. Like it's such a small program, you can't really tell a difference in.
Sure, but just
so
knowing it's qubits,
neat knowing that it happened.
Hood. Yeah. That's, I mean, the implications of scale, affordable quantum computing is going to be really interesting in machine learning spaces, but it's still so prohibitively expensive that it's still in the academic realm, but it's getting there.
Actually, now that you bring up games, so what was it? It's Watson, right? So IBM's Watson was able to learn chess because chess is very deterministic in what you can do, what you can't do, and what is winning strategy.
Data set for chess.
What was that?
They have like chess is notable in games because it has like millions of recorded games, like games from like the 14th century. So it's very good for that type of thing.
So, but the thing is, the thing that I find interesting is the data issue the reason why they have a problem learning Go, or is Go that much more complex over chess?
It's complex, much more complex than chess. Yeah.
Okay.
It's famously, I think, considered the most complicated game ever made. Well, I don't know if that's definitely true, but
there was a recent video about Magic the Gathering, and well, one, they proved that Magic is Turing complete, and then two, that it is absurdly difficult. But if you guys, the documentary on AlphaGo and what they did to train that neural network is super, super interesting. I remember the notable part, and you were sort of talking about it, they got to a point where there were multiple versions of AlphaGo in existence at one time, and they started playing games against each other. And I mean, and spoiler, like the model eventually, they do find a way that it beats like Go champions. But now the Go champions are super interested in it because it started making moves that like went against all like conventional wisdom. Like you should not be playing here. But after like it started playing against itself, so like it was no longer bound to like the moves that they would make, and they were like, okay, what is happening here? They got super interested in it. It's really interesting.
That is really cool.
Way back in high school, I was part of the student technology leadership program back in the 90s, so everything was still kind of like super new. And for fun, we set up a computer so that we disabled all ability to exit apps. Like you couldn't exit a program. And then we took 2 instances of Risk, the computer game, and had it set to the expert level and had them play against each other. And so what we ended up doing was developing a way that you completely lock up someone's computer because neither one will ever win.
Wow.
So you just have this computer, high school, it's like a senior prank thing we did. So we put it on everyone's computer in the entire school. And we had Risk just going against each other. And the only way to get out of it was, hard boot your computer. But
yeah, you gotta be careful. Don't you remember in the movies that started a thermonuclear war?
Yeah, it did.
You gotta be really careful with that stuff.
Yeah.
That's
like to play a game?
Is that? Oh no, I was thinking of what you call it. What is it from Terminator? Skynet. Yeah.
War Games was the Whopper.
Yes.
Joshua.
I should invite y'all. So like with the cohort at TA, every couple of weeks we do a movie night where I'll stream. Like last time I streamed Hackers.
Nice.
So we'll stream and we'll get a
Old
chat on it.
school.
Yeah, and we'll
Hack the planet.
it's interesting watching
Trashing our rights.
once you like know how bad it really is.
Yeah, I know. It makes no sense at all.
Kind of funny to hack.
But that's kind of what makes it fun.
You don't fly around inside of server clusters when you hack?
Only on Thursdays.
Okay. Because I
But it's
see
Friday,
electrons moving around as I fly around and look for garbage files.
You should see a doctor about that, Kent. That's actually
Yeah, that's not good.
I think it's that. Yeah, I think it's that name we had earlier, peyote. I just keep drinking it, so it's okay.
Yeah.
I
thought about that
conversation. Brian said, "What do you call it? The Pekatron?" And I'm like, "Wasn't that the main antagonist in Transformers? What is
No, that's Megatron.
That's Megatron.
Nah, it's definitely Pekatron.
Or then there was Galvatron.
No, you have Megatron and you have Petatron. You have
I did think
the
about
lesser known antagonist.
how cool it might be to like debug code in a virtual reality environment. Like you can walk up to like what it's doing wrong and like just physically grab it, spread it open.
Beat the shit out of it.
It has the
Some
code.
lawnmower man.
It has the code. And you
Damn
can
it!
really just like walk down a road to the
Hadouken.
entire stack. Like just walk down this little road where each section is like the entire stack of what's going on, and you can just like.
I
It's
really
like
like
minority report
Yeah.
stuff going on.
I think
It's
that
like
would
a
just stress
kid
me out.
blame, so you could like bring the person who screwed it up in there and beat them up with their
Look
code.
at this. You see this?
Look what you did to me.
yeah, very very Ghost in the Shell.
I was happy 10 minutes ago.
Brian,
That's Git blame. That's definitely Git blame.
interested to know, Brian. I've been working on one of many side projects. I built this domino game because I'm obsessed with the game Dominoes. I might do a Brownbag about that, to be honest. And after I built it, I was like, okay, next step. This is like my first foray. What if I just make 4 computer players, and what if I just have them play like 100,000 times just to see sort of how that turned out? That was kind of cool. Fun surprise fact, guys. Person who plays first probably wins. But then I started getting really interested in sort of like, how do I improve the logic of the computer players? Because like there's sort of a very basic set of rules as to this is probably more optimal than this is probably more optimal than that every human player does.
Yeah.
But at a certain point, it's, I don't know, like I was really interested in seeing just, that was going to be sort of my exploration into ML, how I could gather data from human players. And
look into GANs, online GANs, and you can play some really fun stuff with that. That's basically how they taught neural networks to play StarCraft, was by essentially using that exact technique, putting a bunch of adversarial online nets and have them play each other for thousands of hours.
So
at first I thought you were talking about Gantt. I was like, oh, I just was asking.
yeah, that's what I was thinking.
Gantt.
That's what I just said. That's actually, yeah, that's where my name comes from. I'm generative adversarial network technology.
I love it.
Explain
I'm not
to
even
me.
real.
Acting like a
That's
robot.
not actually your name. It's just a stage name.
Yeah.
My name's real name's George. My name.
it's yeah.
So I guess that kind of brings up an interesting question. Like, could you use an AI to kind of pull apart the fundamentals of a game in a sense? So, like, all right. So, I am of the mindset, and this is going to kind of be weird or nerdy or whatever. Oh, yeah, I'm of the mindset that a human cannot beat a computer player at Street Fighter because of the nature of fighting games, and there's things built into fighting games to allow humans to actually play them. I kind of don't know. I don't know if I'm going to actually do this, but I was just this kind of brought up the idea of, like, if you were to have a bunch of computers play, and then you kind of analyze the data that they produce, could you kind of like, is it practical to extrapolate like fundamental things directly from that. I guess they kind of do that. I don't know. Is this something that was kind of?
I think you could. Yeah.
Mm-hmm.
The computer can definitely beat people. I dropped hundreds of dollars at the arcade back in the day on Street Fighter.
I mean, to be fair, they cheat.
They do cheat.
Yeah.
But I mean, the funny thing is that I mean, that is actually a fun thing to conclude on. One of the more interesting side effects of a lot of these active models is sometimes they will learn the thing you don't want them to learn. For instance, maybe the best way to win a game is to do nothing, and then they just win by sitting in the starting block and let everybody else play until they all die.
Oh, you mean like data?
Yeah, exactly. So like you definitely have to be a little cautious about the kinds of outcomes models start to generate, because they can learn weird things like how to cheat or how to lie, for instance.
Ooh, that's fascinating.
Yeah.
And then we get Skynet.
Right.
Yeah.
Best way to protect humans is just to have no humans. Or have one, put them in a cage, get rid of the rest, and then we're good.
I mean, that was the whole premises of HAL, right? Like HAL was presented with the question of how do you protect the ship, and it was get rid of all the humans.
Right.
Yeah.
Like, well, the ship is okay.
Yeah.
You'll know we're in trouble when the CAPTCHAs start changing to which person looks like they would make a great battery for the Matrix. That kind of stuff.
Click on all the places humans would take shelter during a revolution.
I mean, I feel like if you asked an artificial intelligence now, like you gave it all the data and you asked it, what's the best way to save the planet? Its answer probably would be get rid of the humans.
Somebody should ask GPT-3 that. See what it says.
I'm pretty sure
don't.
like humans would say that too.
Yeah.
Honestly, because humans have been saying that for a while.
True.
And that's the difference between having an AI just give you an answer versus programming an AI to do something based on the answer. Because if it gives you the answer like kill all the humans, okay, whatever. But if you program it to act on the answer that it gives.
True. Awesome. Well, I got to bounce, everybody, but this is fun. If you have any other follow-up, definitely ping me anytime. Always happy to answer questions. Or if you,
I appreciate
Bye,
it.
guys.
Thank you so much, Brian. That was amazing.
See ya.
Yeah.
Go time.
Yay. Do I just stay to see who stays?